So we want to be sure to have appropriate mechanisms that are in place in order to handle um, cascading interrupts. And as we recalled, we'll need a new process register. And we want to use this in order to recognize if an interrupt is currently in process. So in order for us to advance to the interrupt macro state, we want to set IE to 1. If it's not set to 1, then we do not need to worry about going to the interrupt macro state. And once we get into the interrupt macro state, then we will turn off the IE bit. And then this will allow for us to change that status before fetching the next instruction. So we'll need 2 instructions, EI and DI, and in this we'll set IE to 1 and 0. And then we'll use EI after pushing K0 onto the stack. And so how is this represented in our finite state machine? So we have our advance into the interrupt macro state if int is set to 1 and IE is also set to 1. So we've been able to incorporate new instructions to turn off interrupts. So this will disable the interrupt, and then we have a new instruction as well that will allow for us to enable interrupts. If IE is set to 0 and int is set to 0, then we don't advance into the interrupt macro state. So this allows for hardware to implicitly turn off interrupts while we're in the int state, and this allows for the handler to be given control. And so in essence, what does this do? We have our handler able to save the state of K0. It can enable interrupts. It can execute the appropriate device code. We want to restore our processor registers, disable interrupts, restore the value in K0, enable interrupts, and then return to our original program. But what happens if an interrupt occurs before our return to the original program? We can handle this by having an appropriate jump to address K0, and that can be accomplished using our jump instruction. But sometimes we see that an interrupt can occur at any given moment, which might result in K0 not being saved properly. So what do we need to do in this case? Well, what we'll want to do is make sure we restore K0, enable interrupts, and then return to our program. And so in order to do that, what we'll want to do is introduce a new instruction, RATI, and this will enable interrupts, atomically enable interrupt, and it will set the program counter to return from the handler. So how does this instruction look for us? In this sense, our value in K0 is stored and EI is set to 1. And so with this sequence of instructions, we're able to return appropriately from an interrupt with an appropriate check. And so now we can further update our finite state machine to incorporate these three new instructions that we have here. So we have our EI, we have DI to enable and disable our interrupt. And then we have our RATI instruction that will allow us to return from interrupts. And so during the interrupt microstate, we store the value in the program counter to K0. We have a new program counter value that gets stored into PC, and then we are able to disable interrupts. And so this way we've been able to introduce a number of useful enhancements. Specifically, we have appropriate instructions that enable interrupts, disable interrupts, and also return from interrupts. And then you want to keep in mind that upon an interrupt return, we're storing the current program counter implicitly into register K0. This allows for interrupts to be further disabled, and then we set the program counter to the address of our new handler. And so upon returning from an interrupt, we store the new value of K0 into the program counter, and then we're able to enable interrupts appropriately. And so let's take into consideration that thus far we've presented interrupts, traps, and exceptions. What exactly do we need specifically for external interrupts? We've talked about specific architectural enhancements that are able to deal with these discontinuities. So let's also further discuss other mechanisms that might be needed for handling external interrupts. And so how exactly can we handle external interrupts? What do we need to take into consideration? Well, we know that we're going to need the processor to take on somewhat of additional work in order to process the interrupt and dispatch appropriate ways to handle interrupts with our devices. And so in order to take that into account, let's kind of take a look at how this is represented in a circuit. And so you want to keep in mind that in an electrical circuit, we can have either wired or other logical components. And so here we have an appropriate processor with our data bus active. And then we have our int being represented. And then we have a integer int a line, which can be used within the macro state for our interrupt. And so if you look at this specific wiring, you want to make sure that you pay attention to the way that the int wiring is represented. And we have connections within A to device 1 and to device 2. So this provides for a generalized design to allow for multiple int and int A lines to exist on our bus with connection to the processor. And what we want to do is ensure that we have appropriate priorities or priority levels that are set for each of these lines. So what exactly happens? The device asserts the int bus, so it's wired so multiple devices can access it or assert it simultaneously. At the completion of the current instruction, the CPU will see the int signal and the microcode cycles into the int macro state. So then we have the microcode raises the int A signal line. And this allows for devices to pass through the int A signal if they're not being interrupting. Otherwise, the first interrupting device will assert its ID onto the data bus. And then this further allows for microcode to read the data bus and use the ID as an appropriate index. Once this is identified, we're able to determine which entry into the IVT vector to use to set the program counter. And so with regards to implementation, we're able to have various priority levels that can be set. And so here we have from starting with int 1 and int A1, a priority level of 1. And this can go all the way up to a priority level of 8. And so how exactly can we represent this appropriately with our priority encoder? So you want to keep in mind that the priority encoder will take 2 to the n input and it'll produce a 1-bit int output, as well as an n-bit ID output. If any of the input lines are high, then PE asserts the int output. The PE will assert the encoded value of the first high input line onto the ID output. So if input is 5 and 7 are high on a 3-bit PE, then it asserts int and ID equals 101. If only input 7 is high, then it asserts int and ID equals 111 for the 3-bit PE. And so here we can see how the processor will receive the vector from a keyboard and mouse or any other type of external device. This is done through the interrupt vector table. And so that's going to be set by the OS initially. And this will contain the address handlers for our external interrupts. So whenever a device doesn't know where in memory its handler code is, it can simply refer to the table entry that contains that address. So in this case, we have a keyboard and a mouse, and we can see that the keyboard address is being stored in the vector at position 80, and the mouse is going to be stored at position 82. So once we receive the appropriate NA signal from the processor, then the device can put its vector on the data bus. It's important to keep in mind that during this time, it's still going to be in the int macro state. And so in this case, it's also important to keep in mind that the IVT size can vary based on the operating system. That's going to be a design decision based on the OS. And so where do we want to save or restore CPU registers in the interrupt handler? We can do this in could it be the user stack? Um, that might be a bad idea. The user doesn't even um, have to set the register value if it doesn't feel like it. So it could be a bad practice for having the user set the system stack. What might be some other options to consider? And so in this regard, we can probably deduce that we're going to need a special stack in order to accomplish this. And so the OS, the operating system, is able to have its own system stack that can be utilized in order to handle it. This allows for us to incorporate both a user stack as well as a system stack. And so how would you handle two stacks? Well, if we're going to enter into an interrupt state, what we can do is have the finite state machine switch to our appropriate system stack versus the user stack. And so making use of the stack for saving and restoring, there are some things that we want to keep in mind. Hardware is not going to guarantee the stack behavior by the user. And so we can equip our processor with two saved stack pointers. Once we encounter an interrupt, we can save the user stack pointer from SP, and then we can restore the system stack pointer as well. And so in order to accomplish that, we'll need a merger of two registers. So we'll have a USP, and we'll also have a register for the system as well for SSP. And so there are some considerations that we want to keep in mind. And that means that we can use the system stack for saving appropriate information. And then upon completion of the interrupt, we can restore the registers appropriately. Then we restore the user stack pointer by reversing earlier swaps. And we want to be sure to keep a user kernel mode flag to return whether we're using the user or the kernel stack. So this is a trade-off that we have to keep into consideration. And so how exactly would this be handled? When we start the program, we'll have our user stack, and that's going to be in user mode. If we encounter an interrupt, we would go to the handler, and then we'll switch to the kernel stack. And so we'll be in kernel mode. And then if we have another interrupt, we'll still be in the kernel stack, and it's going to be in kernel mode. Then if we return from our interrupt, we're still on the kernel stack in kernel mode. And then we do another return from our first interrupt. We return to the user stack, and now we're back into user mode. And so this represents a number of different changes that are required. In our interrupt macro state, we're going to store the value into K0. We're going to assert int A and that we're going to acknowledge the interrupt. We'll receive the interrupt vector from the device on the data bus, and then we'll store the interrupt vector into our program counter. We'll push the mode onto the stack, and then if we're in user mode, we'll go through our instructions and disable the interrupts. For our return instruction, We're going to store the value in K0 onto the program counter. We'll pop our mode from our system stack. And finally, we'll enable interrupts.